Alright, today we're going to finalize step one of the PID tuning process, getting our filter squared away. We're going to look at the filter setup we changed to, take a look at the black box logs on how that looks for vibrations with those filters. We're going to talk about how we got rid of the raw vibration on the pitch axis and some of the things we looked at, from making sure the flight controller was secured, to flying it on 4S to see if it was a voltage issue with capacitance, to switching to the ICM gyro on board with the Luminaire Lux flight controller, and then finally to changing some of the settings for the PWM frequency in the ESC firmware. So where we last left off, I was talking about the filter setup here, and we did some flights on that to see our vibrations, and we ended off with looking at the raw noise on that and talking about shutting off some of this filtering. What I really want to do is limit the amount of low pass filters I'm using, and if I'm not turning them off, I want to get them as high as I can. I did a video called Filter Strategies, and I will link that into the upper right hand corner. Check that out. And really my strategy with Betaflight is to use the notch filters on the gyro to crush out any peak noise, and then if I have an ambient noise, I will kill that out with D-term low pass filters. So a lot of times people will go ahead and turn things off one at a time, and you can definitely do that. For myself, I'm using some past experience and past judgment since I've looked at a lot of logs, and I'm going to try to relay that. If you have a noise profile when you look at your raw noise, so in the last video, again, we talked about how to record gyro scale. So record your gyro scale, do the hard flight, and if your raw noise looks something like this, where the amplitude that's really not that high. So this is on the yaw axis. We can go ahead and take a look at the roll as well, and you can see, again, it's really not that high, and we have good control of noise down here from 60 to 200 hertz. It's really kind of just naturally low. This is non-filtered. This is just raw. There's no Betaflight filtering on this. This is direct from the gyro. We do have this peak in the motor bands here, so we'll address that, but that is not that high and it's well defined. Now looking at the pitch axis here, this isn't ideal. We were talking about this before, how this is the amplitude here of how high this isn't that bad. However, this low frequency stuff down here, it shouldn't be there. It should look more like it did on roll, where this just naturally is lower. And I was concerned about that, and I really wanted to address that mechanically. So we did, and I'll talk about what we did to address that. Nevertheless, looking at that, I still felt comfortable that I could jump right into that filter strategy that I talked about in the video, Betaflight Filter Strategies. So I went ahead and turned off my low pass 2 filters, and then I also turned off my low pass 1. Now in Betaflight it has a safety check here saying, hey, you really want to turn off all your low pass filters, and then you have to kind of check it again. And then after you do that, it comes up and says, hey, are you really sure you want to do this? And the answer is yes, I do. Now for your quad, again, you need to be looking at that raw noise and making sure it's somewhat reasonable or somewhat looking like I had it there. The other thing I changed here is changing this down to 60 hertz and change this to 175. And we do want to leave that as biquad. That's key. Generally, PT1 filters, to me, after you really look at them, they don't do much for anything that's not double the cutoff frequency. So that's a good rule of thumb for me, is if you have a PT1 filter turned on, so say I have this on here and I have PT1 and set this for 100 hertz, this PT1 filter is not really doing anything at 100 hertz. It's basically anything north of 200, 250 hertz, it's starting to do some things in reducing some amplitude of the noise, but generally around the cutoff, the slope of the strength of this filter is not very high. So I know we used to use PT1 filters a lot in the past, but biquad is much stronger. It does have a lot more phase delay. It has about double the phase delay. So getting the filter set up as I showed here, go ahead and save that, load it up, and take it out for a flight.
Okay, so this flight is going to be with our proposed filter setup, which is no low passes on the gyro, just the dynamic notch, and then the dynamic low pass 1 on the D term set to 60 and maxes out at 175. So let's see how she goes. Alright, so I want to do a quick motor temp check. Everything seems good there. So let's take it back up. Alright, another motor temp check. Everything is good there as well. So, yeah, we're good.
Okay, so this was the black box from that flight you just saw. And you can see here again on the roll axis, here's my raw noise on the pitch. And when I talk about addressing the peaks of noise with the gyro filtering alone, we got to keep in mind that in that filter tab, there's two hidden filters that we kind of don't see. So when we're looking on this tab here, there's again two filters that we kind of don't see here. First and most importantly is the dynamic notch. So if I go to the configuration tab and I scroll down here, I definitely have the dynamic notch enabled. That's doing almost all the work. There's another key filter that's in the gyro chip itself. It's called the digital low pass filter. And that digital low pass filter is set at 250 Hertz as the cutoff. So anything above 250 Hertz, it is reducing the amplitude of the noise before it even exits and goes to beta flight. Now we can't see the before and after on that because it's kind of done in the gyro chip itself, but based on tests I've done, it does a pretty good job. There's documented phase delay with it for about 0.98 milliseconds, and for that 0.98, it's really sampling it down pretty well. And how do I know that? Is you can put your gyro into experimental mode on an ICM gyro and see how much noise comes through in experimental noise, which moves that cutoff up to 3 kilohertz versus the 250 hertz. And you can see, like, wow, for that 0.98, it's really crushing out a lot of noise. So there is a low pass filter on the gyro. We don't have any beta flight low pass filters here, but we do have the built-in one in the gyro chip itself. And then the dynamic notch beta flight's coming up and cleaning the rest of it. So when we switch back to here, that gyro internal low pass filter is set right at, like I said, right around 250 hertz. So anything above here, it's attenuating here somewhat, but these low pass filters, until you really get double the cutoff frequency or triple the cutoff frequency, that's where they really start to become strong. So if we wouldn't have that internal gyro low pass filter, the digital low pass filter I talked about, you would see a lot of noise at 8,000. You would see tons of noise. It would be huge amounts of vibration, and you can see that for yourself. Put it in experimental mode. Maybe I'll do a video on that some other time. So the internal low pass filter in the gyro is taking care of all this stuff up here. You can see it's all reduced down pretty nice. But we still have this motor band, and that motor band just unfortunately is just right around the cutoff of the gyro's internal digital low pass filter. So we need something else, and that's what the dynamic notch is doing. That's coming in and crushing this out. So let's see how well the dynamic notch did now that we don't have any other beta flight low pass filters on. We only have the one in the gyro chip, and then which we can see what it did here. You can see this is the end result after it acted because of the raw noise, what came into beta flight. And then for what the dynamic notch did, all we have to do is run this gyro roll, and bam! What the f you can see how the dynamic notch just killed out any remaining peak noise. So again, raw, bam, gyro. So the dynamic notch does a great job. And what led me to this strategy is if you record a different debug mode. There's a debug mode called FFT_FREQ, and I'll put that on the upper right hand screen here. And if you do a flight with that on and do have, some sort of low pass filters turned on within Betaflight on the gyro itself, so you'd have the dynamic notch and then some of these turned on. In that debug mode, you can actually see what the low pass filters are doing versus what the dynamic notch does. It kind of parses it out so you can see. And I noticed on there that even with a bunch of low pass filters on here, they're not really doing much. Like it reduced the amplitude, by a little bit. And then after the dynamic notch came through, it really killed it off. Now let's look at our problematic pitch access. Now the pitch, here's our raw, and you can see we have all this scattered noise down here that really shouldn't be there mechanically, so we have to get that addressed. And then we go to the pitch on after it's filtered. And you can see it crushes out everything here, but since the dynamic notch doesn't really go that low, this is still down here and it's just problematic. So you can see with that flight, even with this noise here, everything was fine. There's no flyaways, motor temps were fine, but I still wanted to address this because if you look down here on this trace 0, like we talked about before, and you look at the D term, the red line is, so let me take this down here, the red line is the roll axis and the cyan line is the pitch axis. And you can just see the amplitude difference between the D term for the roll, which is well filtered and well contained, doesn't have that weird ambient noise, versus the pitch. The pitch is still just a mess. It's always dominating. So what would happen is if we don't address that, the pitch is going to kind of limit what we can do for the D term, right? Because it's boosted up pretty high here already. Whereas if we could get the pitch axis to look more like the roll axis in relation to the amount of noise and then how much the D term amplifies that would be better. I mean, you can just kind of look through here and see how the pitch axis is just so much more of a mess than the roll axis. And we can run a spectrograph on each. So this is the pitch axis spectrograph of the D term. You can see all this stuff down here that really got amplified versus the roll axis right here. Now, a lot of stuff I see in questions and concerns, everybody has issues with their quads, and they think it's, Betaflight or something, and it's like, no, it's not Betaflight. It's your quad, one way or another. We just got to figure out what that is. So, went through a bunch of stuff on this, and some of the things we went through, and I have a little list here. The first thing I was concerned about was it was just a capacitance issue. So, I went ahead and flew the rig on 4S. It was a real pooch with those 1750, I think it is, kV motors. But it flew and didn't change anything. So that wasn't it. After that, the Luminaire Lux has an ICM gyro chip on it. So I went ahead and switched to that by going to the configuration tab, and then down here you can see there's a first and second gyro. I actually need to switch it back here. So I went ahead and switched to second, which in the documentation would be the ICM chip. Went in, recalibrated, and rechecked that all the alignment stuff was in good shape for when it was moving back and forth, and then went ahead and flew that. Now looking at the ICM, it was a little better on the pitch axis. You can see if I switch here, this was the MPU 6000. However, when I looked at the raw noise on the roll axis, it was a complete mess. So a little bit further investigation on that, like why is it so crazy? If I look at my roll axis here, where those spikes are being generated is whenever I would enter into a sharp flip or roll, turn some of this off up here, you can see the ICM gyro was just spiking on this board for some reason. So you can see these big spikes. So this would be on a sharp, you can see here, throttle down, sharp roll to the left. It would just spike up and it would be consistent doing that. It was only on the roll axis, not on the pitch, and I don't really do super sharp yaw moves. But whenever I do sharp, that would occur. So on this board specifically, you can see, and it would only really ever do it when I would drop throttle to 0% and then do a real sharp move. But on this board, to me, it looks like the ICM gyro is no good. Now, I don't know if that's other Luminary Lux boards as well, but on this specific board, it was a no-go. The next thing we did is talking to the builder of the quad. He said, well, maybe it's the GoPro mount. Took the GoPro mount off, did a bunch of flights there. And then ultimately, there was the flight controller and the stack, and I'll show a picture, which just kind of, it has the rubber grommets, was pushed down over the nylon standoffs, and it didn't have nuts on the top. So put nuts on the top just to make sure that that was secured down. And I thought that was it, because the flight after that, it seemed to be better. But I made the cardinal mistake of changing two things at once. So I did put the nuts on the top of the stack, and then also changed the PWM frequency in the ESC software to 48 kilohertz. It was defaulted at 24. Ultimately, long story short, that was it. So here's the pitch access, the raw noise, gyro scaled, on a flight with the flight controller stack secured, GoPro mount back on, all that kind of stuff. And you can see we still have the ambient noise down here, the high level ambient noise down here. And that's at 24 kilohertz for the ESC PWM frequency. And then here is the same. These were basically back-to-back flights. This is just changing the PWM frequency to 48 kilohertz in ESC firmware. And now you can see how that's dropped way down, and this is much more defined on the pitch axis here. So now the pitch axis is looking very similar to the roll axis. If I click on that and see that spectrograph, and it's much more well defined. We don't have all this high frequency ambient noise down here. And then also look at our D term traces again. I can scroll this down, hit this little plus here, and we can see that the D term on the pitch versus the roll, it's not like one is dominating. You know, they're both kind of noisy right here, and but it's not, you know, before the one was really prominent, the D term was all kinds of spiking compared to the roll axis. Now they're kind of in line. So now we don't have one axis dominating and limiting our tune. You know, we kind of have both, some equivalency there, which is what we want. Now looking at that another way, this is using the PID toolbox and putting them in a spectrograph for the waterfall. So this you can see is the frequency here on the horizontal, and then the percent throttle along the bottom, and then how you have, this shows that this is kind of a heat map, so the brighter, the more white this is, the higher the amplitude of the noise. So you kind of get three things instead of just two in the previous graphs. And you can see here on the pitch axis for the raw noise how we had all that ambient noise regardless of percentage of throttle. It was just everywhere, all the bottom through, and this is after it was trying to be filtered out, and it's, you know, still there. You know, it was less, it was getting filtered some, but still there. Now this is at 48 kilohertz, and you can see it's much more well defined. It's not even there to begin with on the raw, just like it is here on the roll. So you can see how the pitch and the roll are looking much more similar down for the low frequency noise here. Now both of these again had that filter strategy applied where we don't have any Betaflight low pass filters on the gyro, and this is just the gyro. This is unfiltered, filtered, unfiltered, filtered. And then we do have low passes on the D term, but that's not really being shown on these graphs. And for what I'm talking about in the ESC firmware in BL Heli 32 suite. Now if you have BL Heli S ESCs, you don't have this PWM frequency option. So if you have BL Heli S, this is not something that you can go ahead and change. It might be a reason why you might want to upgrade to BL Heli 32 ESCs, but this by default is set to 24, so we go ahead and ramp that up to 48. Now do note, in Joshua Bardwell's one video on trying to solve some vibration issues, he found the opposite, where at 48, once he changed it back down to 24, he noted it was better. So try it either way if you're trying to figure out some noise. Whoop, scene change, it's the next day. So one of the big questions that comes up next is, how do I know when I have too little filtering? Well, one of the big answers is if your motors are getting hot. That's too little filtering, you need more. On the flip side of that, how do I know if I have too much filtering? Well, the question is, can you turn filtering off without your motors getting hot? In my experience, motors for a 5-inch don't get hot that quick. My quads, I can throw a ton of noise at their motors and they don't get hot. Even on the 6-inch, they weren't even really warm. So then how do you know? Well, you really got to go back to Blackbox for this as well. So we're going to switch over to Trace Setup 3 on my UAV Tech template here. So this has PID error, then your P and D terms, and then on the top row I also have throttle so I can see what throttle value I'm at up here. Looking at it in relation to PID error kind of normalizes how far you're off set point. So let's just look at one of these traces up here. If I zoom in here a little bit. So if the gyro is following on 0 here, this PID error trace right here, if this is on 0, this dashed line, that means the gyro is following the set point. You might be in a hard 180 roll, and if this is PID error 0, that means that the gyro is tracking the set point, which is exactly what you want. So in an ideal scenario, this PID error stays and tracks 0 the whole time. And when you look at it in relationship to PID error, it's kind of nice because then you can see how the P and D term are reacting to the gyro not following the set point. So what we want to look at here is that reaction, specifically the D term. The P term doesn't really have a lot of adverse reaction to noise. So you can see here's the P term, sure it jiggy-jags up and down a little bit, just like the PID error, and you'd see the same amount of vibration in the gyro signal, and then it's, the PID error is just the set point minus the gyro. It's basically the difference between the gyro and the set point. That's what the PID error is. It's very simple math. And the P term is how far that is off of 0 here, multiplied by the gain. So all the PID loop is very, very simple math, and it's basically addition and subtraction and a little bit of multiplication. However, the D term, whatever the slope of these vibrations, see how if we look at this really close here and goes up and down in this PID error, you can see that that slope is going to magnify with the D term. So this is sharply going up, so the D term sharply spikes way down. And if you have a lot of high frequency vibrations, the D term kind of goes crazy. And if you look right here, you can see that example. Right here, the quad really is just, has a little bit of PID error. It's not exactly following set point, but it's basically supposed to be going right across here consistently. But then there's these vibrations in the gyro signal, and look how that little bit of vibration here really makes the D term spike up and down. Well, that's the D term magnifying the vibration. Now we can see the frequency of that just by using the mark point and then stretching out, and you can see that's at 250 hertz. So how do I know if I have too much or too little filtering? Well, I go to section in the log where I'm doing hard 180 turns for prop wash. Prop wash is the holy grail to me. If you can get your tune well suited for prop wash, that's the first major step. We're going to talk about that in the upcoming steps here for the PID tuning principles. So I want to see how is my D term reacting to this set point or the PID error going up and down. So you can see here I'm at set point here, I'm going off, now I'm crossing over, now I'm the other way, kind of overcorrected, so on and so forth. It's going back up and down. See, looking at this PID error line here. And you can see how the D term is reacting as the PID error goes up. The D term tries to push down to get it back onto set point here, back onto 0, and then vice versa. But you can see how the D term has these oscillations, these vibrations in it. So although this is coming down, it's trying to kind of arrest it so it doesn't overshoot. It's like going up and then saying, nope, go back down and up and down. So the D term is not giving a very consistent answer. And I've talked about this before. I equate it to somebody giving you directions and saying, hey, I'm going to go up here and make a left, and then they're starting to double guess their own directions. No, I think it's a left. It might be a right. Wait a second, and the next thing you know, you missed the turn. Now the analogy for too much filtering is somebody saying, hey, you needed to make a right turn back there. They gave you a firm and consistent answer, but it was too late. So you want to have enough filtering that you can have a consistent D term direction or reaction. In this, looking at these traces and some of the experience I had, this is a little light. I think I could use a little bit more filtering here. Just these little jiggy jags that the D terms going up and down throughout here. I would like to see that a little bit smoother. I think where I am mechanically is good. I'm seeing what I'm supposed to be seeing, where there's naturally just a trough between 100 hertz and 200 hertz, and there's no raw vibrations there, and your peak vibrations are really from 200 hertz up. So I think I've covered it. I don't have sporadic noise. Mechanically, I'm good. So the rest now, I'm really left at filtering. That's a big thing. Don't ignore just mechanical issues and try to cover it up with filtering. I could apply a low-pass filter to this, but again, I don't really love low-pass filters because of the amount of phase delay they have. There's a lot of phase delay associated with a low-pass filter and not a ton of gain. So I kind of clipped the log here and you can use your I and O keys on the log. So if I get to this section here with the little red marker and press I, and get to this little section over here and press O, I can just kind of look at this spot. I'm going to go ahead and flip back to my trace setup 0 here. I'm going to look at the raw noise on roll. Now you can see here, and I brought the amplitude way up, so I brought this way up so I can kind of see it. When you're at a smaller section of the log, you typically have to do that. And you can see this is in the raw noise. I have this spike here. Now this is unfiltered, and in the gyro after that's filtered, that's all crushed out. But if I go down to my roll on the D term, you can see some of that's still there. Although it crushed it out, now we're really starting to thread the needle. You can see some of it's still in there. So one of the things I'm going to try, but I'm not going to do it now, I'm going to move on to the next step with where it's at right now, is I'm going to try adding in a static notch right on top of this. So right around 200, I don't know, 260, 275, right around here, I'm going to put a static notch right over this. And what's leading me to that conclusion is if I recalled looking at the waterfall graph on the roll axis here, and you see this big bulge here as soon as we hit that resonance frequency. So I'm going to put a static notch right on the resonance frequency just to give the dynamic notch a little bit of extra help right there. I also like a notch filter solution there, or something to at least try, because it's 0.5 milliseconds of phase delay, whereas if I turned on any kind of low pass filter, let's just say I did a static low pass filter, and really to get any kind of strength out of it, I'd have to be, I'd probably put it at 150 maybe. That's 1.1 milliseconds. Say if I even move that up, so say if I put it at 250, that's about 0.6, but 0.6 is still more than 0.5. So some things I can try with. What's really nice in Betaflight is either the static notches or the low pass filters. You can adjust those in the OSD. So we're going to move ahead with this and tune out the PID loop. After I get the PID set, PID, and I'm really happy with that, we're going to go ahead and do prop wash runs, and then we're going to go keep in mind about this filtering and do some runs with it off, with the static notch on, and maybe I'll even give it a low pass a try and see if one's better than the other. See, kind of the proof is in the pudding on whether we should add in a little bit more filtering or not. I feel comfortable that the big picture with the filter tune is done. I feel like I've minimized as much as I can. I feel like I've chased down the mechanical stuff, addressed that. You're always going to have some sort of low pass filter on your D term, just for how it reacts to higher frequencies noise. The higher the frequency noise, basically the double frequency of any noise that goes in the D term, the double the amplitude of its reaction. So you're going to need some sort of low pass to counteract that. So I have one dynamic low pass filter on the D term. I have just the dynamic notch on the gyro. Really felt I've minimized that as much as I can, so now it's moving on.